Hello and welcome to the presentation of the paper titled Decidability in Group Shifts and Group Cellular Automata. My name is Béaur. I am a master student at the ENS Paris-Saclay, France, and I will be presenting this paper in cooperation with Professor Kari from the University of Turku, Finland. Our contribution belongs to symbolic dynamics, which is a sub-branch of dynamical systems, studying discrete systems. First, let me give you the fundamental definitions necessary for this talk. Let's consider a finite set S that will serve as a state set, generally represented as a set of colors. Then consider a d-dimensional grid, Z to the d. A configuration is a coloring of the grid with the state set. Thus, it can be seen as a function which assigns a state to each point of the grid. That is why we will denote the set of all possible configurations by S to the ZD. A pattern is then one coloring of a finite shape. Now, an interesting point is that there exists a topology on the set of configurations called the prodiscrete topology. One way to define it is using a metric such that two configurations are close to each other if they are agreeing on a large neighborhood of the origin of the grid. It must be remarked that shifting a configuration along any vector does not fundamentally change its properties. Thus, we will need structures fundamental to symbolic dynamics, subshifts. A subshift is a subset of the set of configurations which is topologically closed and invariant by any shift map. Classical examples of subshifts are the ones defined by forbidden patterns. Given P a set of patterns, we can define the set XP of all configurations in which no pattern of P appears. For instance, let P be the set of the two following patterns. Then, this periodic configuration is a member of the subshift. No pattern of P will ever appear in it. In fact, this example is not innocuous. Any subshift can be defined by a set of forbidden patterns, potentially infinite. Thus, as you can imagine, among every type of subshifts, one is particularly studied, shifts of finite type, for which there exists finite sets of forbidden patterns defining them. They can be finitely described, which is necessary for computability questions. During this presentation, knowing or building a shift of finite type will mean knowing or building a finite set of forbidden patterns characterizing it. Now that we can study configurations, we will study their dynamics. Among all functions transforming configurations, two conditions seem to be necessary for a proper dynamical study. First, they must be continuous. The second condition is for the functions to commute with every shift map. This means that shifting a configuration before or after applying a function does not matter. A consequence is that the domains and codomains of these functions are subshifts. These functions are called cellular automata. Although this description is exact, it is absolutely not practical. It explains why cellular automata are studied by symbolic dynamics, but it is not this description which is currently used. There is indeed a most foundational result of symbolic dynamics, called the Curtis-Hedlund theorem, which provides an actually useful characterization of cellular automata. This is the description which we will use during this presentation. A cellular automaton F from S to the ZD to S to the ZD is exactly described by a finite subset N of ZD called the neighborhood and a function mu from the colorings of N to S called the local rule. Then, if C is a configuration and X is a point of the grid, f of C in X is mu of the neighborhood of the point X in C. Let's see how this works in practice. Here we are studying the most famous two-dimensional cellular automaton called Conway's game of life. The neighborhood of a cell will be the 8 surrounding cells and the cell itself. The set of states is simply black and white. The local rule of the cellular automaton is the following. A black cell stays black only if it is surrounded by 2 or 3 other black cells, else it becomes white. A white cell becomes black if and only if it is surrounded by exactly 3 black cells, else it stays white. Let's consider this piece of configuration. Let's compute its image through the cellular automaton. The black cell circled in red, for instance, has 3 black neighbors, and thus, according to our rules, stays black. The white cell just to its right has, in C, exactly 3 black neighbors, thus it becomes black. To know what the whole configuration becomes, we must then have the same reasoning for each cell of C. That is how a cellular automaton works. Thus, the image of the first configuration by Conway's game of life is this configuration. Now that we have described the fundamentals of symbolic dynamics, let's talk about computability results linked to it. The setting I described is pretty general. There is no supposition on the set of states or the dimension. And although cellular automata can be finitely described in this case, many of their properties have been proved to be indecidable, like nilpotency or equicontinuity. Some others have been proven to be decidable only in the one-dimensional case, like surjectivity or reversibility. These results make the study of cellular automata impractical and thus particularly difficult. The only way to obtain positive decidability results on cellular automata is then to restrict ourselves to only certain cellular automata. To do this, we will now suppose an algebraic structure on them. Suppose that the state set is a group G. Thus, by the Cartesian product of groups, we can extend the internal law of G to whole configurations. The multiplication of 2 configurations is the multiplication point by point. We can extend the notion of a subshift to make a group subshift. It is both a subshift and a subgroup, simply. A group cellular automaton is then a cellular automaton and a homomorphism. Of course, we can also extend this kind of algebraic structures to rings. In this case, the structures are called linear. During the last 30 years, linear cellular automata have been thoroughly studied, and it has been established that almost every important properties of linear cellular automata can be decided regardless of the number of dimensions. Thus, the question becomes, how can we extend the results about linear cellular automata? Our proposition is to extend them to group cellular automata. To achieve this, we will study group subshifts, which are the fundamental structures running the functioning of group cellular automata. First of all, there are some classic results known since the late 80s and established by Kitchens and Schmidt. The first one is that every group subshift is a shift of finite type. This means that not only group cellular automata can be finitely described, but their domains too. We can build them. Knowing or constructing a group subshift will then mean to build a set of forbidden patterns characterizing it. For the second result, we must explain the difference between a periodic and a fully periodic configuration. A configuration is periodic if it is invariant by shifting it in one direction. It is fully periodic if it is invariant by shifting in d independent directions. You can see here that the top configuration is periodic only horizontally, whereas the bottom one is periodic both horizontally and vertically, and thus fully periodic. The second theorem of Kitchens and Schmidt is that fully periodic configurations are dense in group subshifts, with regard to the topology we use here. In this context, the density means that if a pattern appears in one configuration of a group subshift, no matter if this configuration is periodic or not, then there exists a fully periodic configuration containing this pattern. The second theorem then enables an algorithm to answer the following question. Given a group subshift and a pattern, does there exist a configuration in the group subshift containing this pattern? Indeed, we can use two semi-algorithms. One lists every possible fully periodic configuration containing our pattern and checks if one is allowed in the group subshift. The second tries to complete our pattern to form a full configuration. If it fails, it means that the pattern is not allowed. These two semi-algorithms semi-decide both the problem and its negation, thus deciding the problem. A significant possibility using this algorithm is the possibility to compare two group subshifts for inclusion. This means that having two sets of forbidden patterns, we can decide if the two generated subshifts are included one in the other, or even equal. Now that we can compare two group subshifts, here is the main technical result of our contribution. For this, we will need to define two different projections of group subshifts. First is the dimensional projection. We can consider that a configuration of dimension d is a bi-infinite sequence of d-1 dimensional configurations concatenated to each other. The dimensional projection of width n of such configuration is then n consecutive d-1 dimensional configurations of the sequence. The projection of the subshift is then the set of all projections of configurations of the original subshift. This dimensional projection of a group subshift is still a group subshift. The other type of projection, called the Cartesian projection, follows the idea that, with two groups G1 and G2, a configuration with state set G1 times G2 can be seen as two configurations concatenated, one over G1, the other over G2. The Cartesian projection is then taking, for instance, the configuration over G1. Then the Cartesian projection of a group subshift, which is still a group subshift, is the set of all Cartesian projections of configurations of the original subshift. Our result is that, given a set of forbidden words defining the original subshift, we can effectively build both any dimensional projection and the Cartesian projection of a group subshift, no matter the dimension. The construction is recursive and alternates between the two projections. Since dimension 0 represents finite cases, this means that Cartesian projection is direct to build, and thus the recursion is initialized. I will provide here an idea of the construction we have. Let's begin with the most important construction, the dimensional projection in dimension d. First, it is easy to test whether a possible pattern for the projection is allowed, because it would also be a pattern of the original subshift. So we can iteratively build an ever-growing set of forbidden patterns. Because a group subshift is of finite type, we know that this construction will, at one point, reach a characterizing set of forbidden patterns. The question becomes, how do we know when to stop? For this, we proceed to a test of extendability. Taking the current supposed set of forbidden words, we can build a left and right projection, which are two different Cartesian projections of dimension d-1. We know how to build them by the iteration hypothesis. If these two projections are proved equal by our comparison test, then we claim that our set of forbidden words characterizes the dimensional projection. Thus, we have built the dimensional projection. Now, let's build the Cartesian projection. Although the Cartesian projection is less important for the rest of the paper, it is essential to make the dimensional projection work, and is a bit more difficult to build. To proceed, we can, like for the dimensional projection, iteratively build a set of forbidden patterns by testing for a possible pattern whether any complementation is allowed. The question is again to know when we have enough forbidden patterns to characterize the Cartesian projection. Our tests rely on the computation of a number n, such that if pi n of xp and pi n of psi I of x match, then the two sets themselves match. Building pi n of xp requires only the dimensional projection in dimension d-1, but to build pi n of psi I of x, we use the commutation of the two projections and thus need both the dimensional projection in dimension d and the Cartesian projection in dimension d-1. Once this is done, we can build the Cartesian projection in dimension d. Now that we can build dimensional projections of group subshifts, how can we proceed to decide properties of group cellular automata? For this, we need group subshifts which characterizes the properties of group cellular automata. The main one we will study is the set of space-time diagrams of a group cellular automaton. Given a group cellular automaton F, a space-time diagram is a bi-infinite sequence of configurations Ci such that f of Ci equals C of I plus 1. This does not mean that any configuration appears in such a bi-infinite sequence. The set of spacetime diagrams of F is a group subshift. Furthermore, it is easy to build a set of forbidden patterns defining it by forbidding impossible successions for such a group cellular automaton. The problem of the set of spacetime diagrams is that it is d+1 dimensional and thus difficult to study directly. That is why we introduce two new subshifts which have less dimensions. The first one is the trace subshift. It is the restriction of a space-time diagram to a finite space. It can also be seen as the projection of a space-time diagram, only preserving the time dimension. Because it is a dimensional projection, it can effectively be built. The other one is the limit set. It can be defined as the set of configurations which can appear arbitrarily late in a configuration sequence. By capacity of the space, it means that it is the dimensional projection of the spacetime diagrams along the space dimensions. We will now show some ways to decide some classic properties of group cellular automata. First, surjectivity and injectivity. For surjectivity, we can use the limit set. Indeed, if any configuration has a preimage, any configuration is part of some bi-infinite sequence of configuration. So a group cellular automaton is surjective if and only if its limit set is the whole group subshift itself. Since we can compare group subshifts and build the limit set, we can then decide surjectivity for group cellular automata. For injectivity, we use the characterization of injectivity for homomorphism. The only preimage of the neutral configuration must be the neutral configuration itself. In fact, there is a way to build the kernel of a group cellular automaton by forbidding patterns whose image is not the neutral element. Since we can compare group subshifts, this means that we can test if the kernel is reduced to the neutral configuration. Injectivity is decidable for group cellular automata. Another classical property is nilpotency. A group cellular automaton is said to be nilpotent if its limit set is limited to only one element. Since the neutral configuration is forcibly in the limit set, this means that a group cellular automaton is nilpotent if and only if its limit set is restricted to the neutral configuration. This means that nilpotency can also be decided. Then, a group cellular automaton is said to be eventually periodic if and only if there are two integers n and p such that f to the n plus p equals f to the n. In fact, there exists another characterization of eventual periodicity. It is equivalent to the finiteness of any trace subshift. The finiteness of a one-dimensional subshift of finite type being decidable, This means that eventual periodicity is decidable for group cellular automata, no matter the dimension. There are also some topological properties which can be decided for group cellular automata. First, we have to explain what an equicontinuous configuration is. C is an equicontinuous configuration if for every finite domain D, there is a greater domain E such that any other configuration coinciding with C on E will always coincide with C on D. A function is then called equicontinuous if any configuration is equicontinuous, and the function is called sensitive if none are. Normally, a cellular automaton can be neither of them, but it is not the case for group cellular automata. Either they are equicontinuous, and if they are not, they are necessarily sensitive. Furthermore, equicontinuity can be shown to be equivalent to eventual periodicity. Thus, these two topological properties are decidable. So, to summarize everything I presented up to now, we established a new method to decide properties of group cellular automata using the construction of projections of group subshifts. This method enables a generalization of many results known about linear cellular automata. However, contrarily to previous methods, this one does not provide any complexity bounds. The results are not practical. Many classical properties are now proven decidable, but other, like transitivity, seem not within the reach of this method. Another question is the generalization to a greater class of cellular automata. This seems difficult due to the critical importance of algebraic fundamental results, which seem difficult to generalize. Thank you for your attention.